Antiferromagnetic. So one day we discussed the Heisenberg model, anisotropic Heisenberg model. I will come back to discussion of anisotropic models at the end of the lecture. So the Hamiltonian which we are dealing with was sum over n not equal to n, j and m, s n, s n. So we discussed the situation where the atom form periodic lattice and each atom has unfilled inner shell, so there is a magnetic moment associated with each atom, and these magnetic moments interact through this simply looking Hamiltonian. Moreover, without losing generality, I considered the interaction between nearest neighbors only, and as illustration, I considered simple cubic lattice. So what we have discussed last time, that if all exchange integrals j and m are positive, then we have a ferromagnetic ground state corresponding to moments aligned parallel. And then we considered the behavior of this model at temperature much smaller than Tc. This is a ferromagnetic ground state, and we have found that the Hamiltonian can be written down as some constant plus sum over q, epsilon q, bq, double bq. So we expressed our Hamiltonian in terms of harmonic oscillator. We have found that dispersion epsilon q at long wave limit was proportional to q squared. This is behavior of a ferromagnetic system, typical for antiferromagnetic system. So today we are going to discuss what happens if all exchange integrals and m, I'm talking about nearest neighbors, what happens in this case. So we expect that alignment of nearest spins will be opposite, and therefore we have bipartite lattice of spins. So we can say that there is a sublattice A and there is a sublattice B. So at this point I would like to mention that not all lattice symmetries are compatible with that arrangement. Namely, not all lattices are bipartite. For example, the simple cubic lattice is bipartite. Two-dimensional hexagonal lattice is bipartite. Namely, you can color it with two different colors, blue and red. However, triangular lattice is not bipartite. Therefore, the state which I'm going to consider now is not compatible with the certain symmetries of lattices and cannot be realized in these lattices. So, talking to magnons, the synonymous of magnons is spin waves. We discussed that this form of Hamiltonian, which actually is written in terms of oscillators, which we attribute to magnons, is also corresponding to propagation of the spin wave. We can think about precession of our magnetization vector, and therefore, with the time, this magnetization vector persists. This is the propagation of spin waves. The question is, what is the Hamiltonian describing the long wave limit of antiferromagnetic Heisenberg model? What is the E node? And what is the dispersion of the antiferromagnetic magnets? So these are the questions which we are going to address during today's lecture. Good. Again, without losing any generality, I'm talking about three-dimensional system. I'm not going to speak about quantum phase transitions, although it's a very interesting question. And I'm talking about lattices which are compatible with a bipartite structure. For illustration, for real calculations, at the end of the day, I will use simple cubic lattice. So now we have two lattices, A and B, two sublattices. So I start with the product of X and Y components. As we did it for consideration of the ferromagnetic state, I still don't see error in the list. Okay. So as we have calculated it last time, this is m minus Sm plus Sn plus Sm minus. However, now I say that one spin belongs to sublattice A and another spin belongs to sublattice B. And I should take care about that. As on the previous lecture, I defined the Fourier transform for the transverse components. This is 1 over square root of n, sum over q, s plus minus q, exponent e to the power I plus minus I q n. And I use shorthand notations. Shorthand notations is denoted as n. The inverse Fourier transform s plus minus q is equal to 1 over square root of n, sum over n, Sn plus minus, exponent minus plus I u n. On Monday lecture, I introduced bosonic operators, beam. However, now I have two sublattices, and I need to introduce two sorts of bosonic operators. Let's do it in the following way. I will write down that S u minus is equal to 1 over square root of 2s a q plus s q plus is equal to square root over 2s s q. This is for sublattice A. And for sublattice B, I will say that SQ is equal to square root over 2s BQ, and SQ plus is equal to square root over 2s BQ done. Why I change these notations? Because I said every time I have a spin flip, and therefore this is usable convention to write down it this way. Moreover, by writing down this way, I will also address the question about zero-point motion and energy of the ground state in a proper way. Good. So therefore, now I'm ready to write down the transverse and longitudinal part of the Hamiltonian, although I assume that my Heisenberg model is isotropic. So, if I do that, the same in the fashion which I did it on the previous lecture, this is minus sum over n, sum over m not equal to n, j and m, Sn minus Sm plus, plus Sn plus Sn minus. Now I will write it in terms of the operators A and B. This is minus sum over m, sum over L. I remind you that the exchange integral depends on the modulus L. So n minus m is denoted as L. So here I have 1/2 because of this 1/2. I have 2s over n. So 2s coming from the product and n coming from Fourier transform. I have sum over q1, q2, and here I have a dagger q1, b dagger q2, plus, well, exponent I q1 n plus I q2 m, and I have term b dagger q2, sorry, b a q1, from this term, which is e to the power I q1 n minus I q2 m. So you see that this Hamiltonian as well as ZZ Hamiltonian is Hermitian. Then I define my structure factor gamma q is 1 over z sum over L I e to the power minus I q L. And I can write down finally my transverse part of the Hamiltonian H is equal to minus S times Z times J sum over Q gamma Q A dagger Q B dagger Q plus B Q A Q. So this is the transverse part. M is cancelled out when you take summation over M, you have a delta symbol. And you have a structure factor since you have N minus M here. The same way as we did it for the ferromagnets. Now, with the same way we consider ZZ, namely, I write down that on a sublattice A, S, N, Z, N belongs to A, is equal to S minus 1 over N, sum over Q1, Q2, A dagger Q2, A, Q1, e to the power of I, Q1 minus Q2. And we derived this expression on the Monday lecture, and in sublattice B, since this is A and this is B, on the sublattice B, S, M, Z, B is equal to minus S, because it has opposite direction, minus 1 over N, sum over Q1, Q2, B dagger Q2, B Q1, e to the power I Q1 minus Q2 M. So, when I write the transverse part of the Hamiltonian, sorry, longitudinal part, H parallel, which is a product of ZZ terms, as in the previous case, I only consider quadratic terms in terms of the creation and annihilation operators. I will drop term which contains 4 operators because it corresponds to interaction between magnons, and I also dropped the same order term, namely proportional to the 4A operators and 4B operators due to the very same reason. So this is only approximation. This is approximation. So H parallel then is equal to minus sum over N, J, N, M, N, M, S, N, Z, S, M, Z. Once again, I'm considering interaction between nearest neighbors, and when I make a Fourier, this is plus sum over n sum over L, GL, and I have term, let me write it here, I open the bracket, so the first term is S squared, I put sign plus, so S minus S squared and minus gives me plus, and then I have term minus S over N. Remember that for ferromagnets we have a 2S over N because we have only one sublattice, but now this is sum of Q1, Q2, A dagger Q2, A Q1 plus B dagger Q2, B Q1 times e to the power I sum over N and L, I Q1 minus Q2 N, and that's it. And there is GL. That's it. Good. So, after combining all terms, no, JL is already here. Sorry. It's too much. I put JL outside the brackets. And there is a sum. Yeah. There is a sum. I don't need to repeat it. Good. Okay. So far so good. Now, by combining these two terms, I get my Hamiltonian. So H, which is H parallel plus H perpendicular. So sum over N gives me total number of spins. Sum over L gives me the number of nearest neighbors. I remember that J, all J's, J, N, M are negative. Therefore, the first term can be written down as plus S squared times N times Z times modulus J. So this is this term with a sign. As I said, J is negative. And therefore sign is minus. This is the same inode which we obtained for the ferromagnets. However, we will get corrections to it. Then I have terms sum over Q you see we have a minus and this is negative, therefore these terms will come with a sign plus. So this is S times Z times modulus J times sum over Q. So this term will give me A dagger Q, AQ plus B dagger Q, BQ. And this term gives me gamma Q, A dagger Q, B dagger Q plus BQ, AQ. So, this is the Hamiltonian. I have two types of bosons for sublattice A and for sublattice B. I wrote my Hamiltonian as a quadratic form. However, this quadratic form is not yet diagonal. Therefore, in order to diagonalize this Hamiltonian, I need to apply the value of transformation. How can I define the value of transformation? I write that I have a new apparatus, I call it alpha q and beta q, dagger, which I expressed in the terms of the operators A and B in the following form. So this is UQ, VQ, VQ, UQ, AQ, BQ, dagger. So this is my matrix. Since I define my operators A and B as bosonic operators, these are magnets and spin waves, I need to request that my new operators alpha q and beta q also satisfy both the commutational relations. If I do that, I will get a condition that determinant of matrix U is equal to 1, which immediately results in the condition UQ squared minus VQ squared is equal to 1. Once again, as I did it before, I assume that U and V are even functions of Q, and these are real functions. This is a conjecture, and after solving my equations, I will see if my conjecture is correct or not. Before it was correct. Here it will also be correct. So, re-expressing operators AQ, BQ in terms of operators alpha and beta, alpha q, beta q, dagger. So the inverse matrix is equal to U. Sorry, for convenience it's better to define minus here and then I have a plus index here. However, it doesn't matter. A, Q, B, U, dagger. So this is UV transformation on bipartite sublattice. That's it. So I have my Hamiltonian, and let me spend a few minutes to bring this Hamiltonian to the diagonal form. Good. So I will always solve the problem what is E node. However, you see this E node will get some corrections to it. The ground state energy. However, what is unsolved is the question about spectrum of the antiferromagnetic magnets. So I will write we have four types of terms. A dagger A, B dagger B, A dagger B dagger, and BA. So I will write all them. AQ dagger AQ is equal to UQ alpha Q dagger plus VQ beta Q times UQ alpha Q plus beta Q plus VQ beta Q dagger. So if I collect terms, I can write it down as UQ alpha Q dagger alpha Q plus VQ square beta Q dagger plus the off-diagonal term UQ VQ alpha dagger beta dagger plus beta Q alpha Q. Okay, then BQ dagger BQ is equal to that. I have all pluses here. So This is U Q beta Q dagger plus V Q alpha Q times U Q beta Q plus V Q beta Q dagger. So this is U Q square beta Q dagger beta Q plus V Q square alpha Q dagger plus U Q V Q alpha dagger beta dagger plus beta alpha Q. So now I have term A dagger Q, B dagger Q. This is U Q alpha Q dagger plus V Q beta Q. This is A Q times U Q beta Q dagger plus V Q alpha Q. So this is alpha. Therefore, I will first write diagonal term. So this is U Q V Q alpha Q dagger alpha Q plus beta Q dagger plus U Q square alpha Q dagger beta Q dagger plus V square beta Q alpha Q. So, and the last term will be just complex conjugated of this one. So BQ AQ. I will immediately write down what it is equal to. UQ VQ. Here I have alpha Q dagger plus beta Q So it's complex conjugated, as I said, it's not Hermitian conjugated, plus UQ square alpha Q beta Q plus VQ squared alpha Q dagger beta Q dagger. Good. So now I am able to rewrite my Hamiltonian in terms of new variables. Let me keep this one. I probably don't need the transformation anymore. I hope I did not make any mistake. It looks like I did not. I will put a line here. So I'm rewriting this Hamiltonian. So H minus E naught is equal to plus S times Z times modulus J times sum over Q. By the way, I will use commutation relations. So this is 1 plus BQ dagger BQ. The same way this is 1 plus alpha Q dagger alpha Q. And the same way here. Here and there. So by collecting terms, I have UQ squared plus VQ squared plus 2 times gamma Q UQ VQ times alpha Q dagger alpha Q plus beta Q dagger beta Q plus 2 UQ VQ plus gamma Q UQ squared plus VQ squared times alpha Q dagger beta q dagger plus beta q alpha q. And then I still have term originating from these connotation relations. So this is plus, and this is 2 times vq squared plus 2 times uq vq times gamma q. So this term doesn't contain any creation and annihilation operators, but as we will see, it will correspond to 0-point energy, like for harmonic oscillators. Good. So now what we need to do is to request that u and v coefficients satisfy such equation that this term should be equal to 0. So therefore, I have a second condition. The first one is uq squared minus vq squared is equal to 1. And the second condition tells me that 2 times uq vq plus gamma q uq squared plus vq squared is equal to 1. So I'm going to solve this system of 2 coupled nonlinear equations in order to find out coefficients u and v, and therefore find out spectrum. So this will be the spectrum epsilon q antiferromagnets. Because if I nullify the coefficient in front of the term containing 2 creation and 2 annihilation operators, the rest brings me by Hamiltonian to the diagonal form, and therefore my task is accomplished. Okay? Good. And as usual, I need to look at the proper sign of the... So, from this equation, I have vq squared is equal to uq squared minus 1. And I take a square. So now I'm writing second equation. uq squared plus vq squared times gamma q is equal to minus 2 times uq vq. So this is equation number 2. So I see that gamma is structure factor. For some values of q it is positive, for some values of q it is negative. Therefore, I will take a convention. So let's consider the domain of q's when gamma q is positive. Later I can consider opposite case when gamma q is negative, but if gamma q is positive, then uq times vq is negative. And other way around. If gamma q is negative, then the product uq and vq is positive. Then I will write it down as 2uq squared minus 1 times gamma q is equal to minus 2uq squared 1 minus uq squared minus 1. So, which means that I also assume that uq is larger than 1. Writing it this way. uq is larger than 1. So now I take a square, and I remind you that this condition is necessary because by squaring right-hand side and left-hand side, I create some additional artificial roots which are unphysical. So in order to deal with the physical roots of equations, I always need to take care about the conditions which I use. So 2uq squared minus 1 squared gamma q squared is equal to 4 times uq squared minus 1. Or 4 times uq fourth. I will put everything to the right hand side. So this is 1 minus gamma q squared minus 4uq squared. Again, 1 minus gamma q squared minus gamma q squared is equal to 0. So I got equation whose solution gives me uq. So we all know how to solve quadratic equations. So uq4 minus uq squared minus gamma q squared 4 times gamma q squared 1 minus gamma q squared 1 minus gamma q squared. You remember that gamma q is equal to 1 over z sum over q e to the power minus I ql, and of course gamma q modulus gamma q squared is always smaller or equal to 1. It's equal to 1 and q equal to 0, and for the rest q it's so. This then is beautifully defined equation with a solution uq squared is equal to, so 1/2 plus or minus square root over 1/4 plus gamma q squared divided by 4 times 1 minus gamma q squared. So as I said, uq is bigger than 1, therefore I take the square root with a sign plus. So this is 1/2. I will write it as a 1 divided by square root of 1 minus gamma q squared plus 1. So dq squared is uq squared minus 1. Therefore, it is equal to 1/2 1 over square root over 1 minus gamma q squared minus 1. Because I took the root which is bigger than 1, and I immediately obtain uq and dq. So I need two other quantities. uq squared plus dq squared is equal to 1 over square root over 1 minus gamma q squared. And the product uq squared dq squared is equal to 1/4 1 over 1 minus gamma q squared minus 1. Therefore, it is equal to 1/4 gamma q squared gamma q 1 minus gamma q squared. When I will take a square root, I will get negative value because the condition is that uq dq is negative. Okay, I have everything, and let me first write down the dispersion. So, epsilon q antiferromagnets is equal to F times Z times modulus J times uq squared plus dq squared plus 2uq dq times gamma q. So, it is equal to S Z modulus J. uq squared plus vq squared is 1 over square root 1 minus gamma q squared. uq dq is equal to minus gamma q divided by 2 times 1 minus gamma q squared. So I have a minus gamma q times gamma q is gamma q squared divided by 1 minus gamma q squared. So it is equal to S times V times modulus J times square root 1 minus gamma q squared. And that's it. So this is energy Q I F. Let me compute term corresponding to 0-point motion. Delta E naught, which is then equal to S times Z times J, sum over Q, 2VQ squared plus 2 times UQ VQ times gamma Q. You see that this is a constant. So this is S times Z times modulus J, sum over Q. VQ squared is 1/2, 1 over square root minus 1. I have a 2VQ squared. So this is 1 over square root 1 minus gamma Q squared minus 1. This is VQ squared minus 2UQ VQ gives me gamma Q. Yet another gamma Q squared is here. It's square root 1 minus gamma Q squared. So again, you see that these two terms collected, and I have square root minus 1. Good. Now I am collecting everything what I get. So, first of all, my H is equal to minus S squared N times Z times modulus J. Then I have this term, minus 1, which, when I take a summation over Q, gives me N. So minus S times N times Z times modulus J. Then I have plus S times Z times modulus J, sum over Q, square root over 1 minus gamma Q squared times alpha Q dagger alpha Q plus beta Q dagger beta Q plus 1. So, this is the Hamiltonian which I obtained. So, let's just look at this term. I can write it as alpha Q dagger alpha Q plus 1/2 plus beta Q dagger beta Q plus 1/2. Therefore, this is N alpha plus 1/2 plus N beta plus 1/2. So I have two independent quantum oscillators corresponding to alpha and beta degrees of freedom, and therefore I have a 0-point motion. As we know, quantum oscillator behavior of particle in parabolic potential is characterized by 0-point motion energy. And this is entirely quantum phenomenon. And then, if I look at these two terms, this is minus S times S plus 1 times N times Z times J. So this is E naught. So I computed everything. And now let's discuss what we are about. Good. First of all, comparison between ferromagnets and antiferromagnets. You see, I was super careful by doing calculations. So I didn't miss anything. I didn't miss term of the order of S compared to the term of the order of S squared. And I got right coefficient S and S plus 1. And I got both spectrum and 0-point motion energy. So, ferromagnets. We got our dispersion For the antiferromagnets, epsilon Q, Q, epsilon Q, Q. 1 minus gamma Q squared. We obtained last time that gamma Q, defined on the top of the blackboard, behaves as, for small q, 1 minus q squared a squared over 6 to the power 1/2. So this is then q squared a squared over 6 to the power 1/2, and therefore this is a over square root of 6 times modulus q. So you see that dispersion of the antiferromagnets for small q is c dot modulus q. So in the ferromagnetic case we have a quadratic dispersion, and this is what I said is very similar to ideal Bose-gas, because for ideal Bose-gas, which is not superfluid, we have q squared over 2n. These are free particles. For the superfluid Bose-gas, for Bose-gas with interaction, we have sound like waves. So what we say then, that ferromagnets are described by the class of the universality of problem similar to the ideal Bose-gas, while the antiferromagnets correspond to the universality class of the weakly interacting Bose-gas. So, while I want to discuss several other important topics and discuss physics, what I leave you to describe and to study and consider at home. So first of all, there is a thermodynamic contribution from the ferromagnetic and antiferromagnetic spin waves. You should do this exercise yourself, because what we did with you and Andre is considering Bose-gas with a linear dispersion. So we obtained actually that for three-dimensional case the specific heat and entropy is proportional to temperature to the power cube. This will be the same effect for the antiferromagnets. However, by simple power counting, since you have a q square and q here, I leave it to you to obtain that contribution to the specific heat and entropy by the ferromagnetic magnets will result in the temperature dependence temperature to the power 3/2, just because you have extra power of q. Do this exercise. Then, another thing is that if we write down the order parameter, the correction to the order parameter for low temperatures, for superconductors, Andrei showed to you that this is exponential term. However, here we have Goldstone modes. By the way, the mode where you have gapless excitations, which is proportional to certain power of q, are called Goldstone modes. On the colloquium on Monday, Professor Wilczek already referred to Nambu-Goldstone theorem, and I'm happy that before this colloquium you already heard something about Goldstone modes. I'm equally happy that when Professor Wilczek discussed Josephson effect, and in particular he discussed so-called AC Josephson effect, namely applying a constant voltage you get AC current. What I discussed with you on the blackboard was a DC Josephson effect, that without applying any voltage you have the current between two superconductors separated by a small dielectric layer. Again, you were prepared to this colloquium knowing what this Josephson effect is about, and I'm happy that you also can understand what Professor Wilczek was saying about ferromagnets. So, order parameter. What is the order parameter for the ferromagnets? For the ferromagnets, we can introduce uniform magnetization, which is non-zero below critical temperature, and which is zero above critical temperature. Therefore, for the other parameter, which is uniform magnetization, we can consider how much this uniform magnetization deviates from its maximum value corresponding to ground state at finite temperature. This deviation is described by the Bloch law, and for ferromagnets, this deviation is proportional to temperature to the power 3/2. Read the book. The best book which I can advise you is Kittel's book, Quantum Theory of Solids. Do your calculations. It's equally good or even better. I gave you everything and all definitions. So, the deviation of the other parameter from its maximum value is proportional to the temperature to the power 3/2. It's not exponential. For the antiferromagnets, what is the order parameter here? As I said, we have two sublattices, and we cannot speak about uniform magnetization anymore, because if we take, uniform magnetization, Mz, will be averaging, proportional to averaging sum over M, S, and Z. It is non-zero for ferromagnets below critical temperature, but clearly it is zero for the antiferromagnets. So instead, we can define so-called staggered magnetization, Mz, which will be difference over two magnetizations n belong to sublattice A, S, and Z, minus sum over M belongs to B, S, M, Z, average. The staggered magnetization will be the order parameter of the antiferromagnetic state. So this is A, B. I take magnetic moments separately sitting on sublattice A and sublattice B, and I subtract one from another. So, what I leave to you as non-mandatory homework is to consider how the order parameter, which is staggered magnetization, deviates from its maximum value at finite temperature. Good. What else? In principle, another exercise which I'm happy to give to you is to take the operator corresponding to the uniform magnetization and operator which corresponds to staggered magnetization and compute the commutator of these operators with a Hamiltonian. You will see that uniform magnetization is commuted with a Hamiltonian. Therefore, this quantity is conserved, as you know from the quantum mechanics. While the staggered magnetization does not commute with a Hamiltonian. And therefore, this quantity is not conserved. Roughly speaking, it means that the ferromagnetic state, which is plotted here, is true ground state of the system, while the antiferromagnetic state is not necessarily true ground state of the system. And 20 years ago, on the age of beginning of high temperature superconductivity, there was a long debate if for two-dimensional antiferromagnets, Néel state, this staggered state has a name of Néel, to appreciate contribution of French scientist Néel, who contributed a lot to the theory of quantum antiferromagnets. If Néel state for two-dimensional square lattice is the ground state or not. And it appeared that although it's not obvious, it is the ground state for two- and three-dimensional situation. There was a theory proven by mathematicians saying that this is correct. The alternative variation of ground state, which was introduced by Phil Anderson, was corresponding to so-called spin liquid state. This is one of the very hot topic nowadays, because now there is experimental evidence that there are systems where spin liquid state corresponds to the ground state, not the Néel state. And this is really a big issue for last 3-4 years. I will come back to discussion of this thing on my concluding lecture the day after tomorrow. What else? Before I come to a few words saying about strongly correlated models. Let's briefly consider behavior of the ferro and antiferromagnets above critical temperature and see what is the difference. Well, maybe not. Maybe before coming to the discussion of above, behavior of above, let me comment a few words about dynamical properties of the ferro and antiferromagnets and their difference. As I said, it will not be sufficient to have a 12th lecture about quantum antiferromagnetism, because when I taught the course of quantum antiferromagnetism, including effects in low-dimensional systems and quantum phase transition in Munich, it took me 20 lectures just for the theory of magnetism. However, I want to tell you some key properties which you can learn more if you would like to specialize in these topics. So, dynamical correlation function. I can define the susceptibility as a function of Q and omega. We have several examples. Separately, I considered the precession of spin or magnetic moment and considered dynamical susceptibility, which doesn't depend on Q and depends on omega. And I considered only static susceptibility, which depends on Q but doesn't depend on omega. Let's now combine two things together. Obviously, if you above critical temperature, I would like to start with the ferromagnets. If you above critical temperature, then you have full spin isotropy. You can think about Bloch sphere, behavior of magnetic moment, and it freely rotates covering whole sphere. Therefore, above critical temperature, chi xx is equal to chi yy is equal to chi zz. Above critical temperature, this is true. Below critical temperature, this is not true anymore, because you have broken continuous symmetry. So this symmetry of free rotation of the magnetization vector on the sphere corresponds to continuous symmetry. And since a sphere is two-dimensional manifold, in mathematics it is called S2, this is two-dimensional surface in three-dimensional space. The group describing behavior of spin is SU2 group, and this is continuous group. So below critical temperature, you spontaneously break this continuous symmetry. Therefore, while your magnetization now has a constant component along z direction. So you don't freely rotate on a sphere, but you can only rotate on the circle. And therefore, depending on, you have two possibilities. You do it up and down, and actually to connect these two states, you need to apply magnetic field. So the excitations corresponding to Z component is then not equal to XX or YY, susceptibility, because you have broken continuous symmetry. As I said, what we see from this picture, then the Z susceptibility is gapped. So therefore, I can write down that this is like minus delta squared, where delta corresponds to this fictitious magnetic field which connects these two sorts of orbits. While the XX and YY susceptibility, which I can combine into plus minus susceptibility Q omega, corresponds to precession. So this is gapless excitations which are ferromagnetic magnets. So therefore, this susceptibility behaves as omega squared minus lambda q squared. Two possibilities corresponds to the process of emission and absorption of the magnets. And as we agreed, in order to discuss a retardant green function, I will move Paul into the lower half plane of the omega. So what I'm saying that the dynamical susceptibility as a function of Q and omega provides you immediately information about spectrum of your elementary excitation. In particular, this imaginary part of this susceptibility is connected to the cross-section of neutron scattering and can be directly measured by the neutron scattering experiment. And you see from this naive picture, in the life, of course, life is more complicated. There are relaxation processes. There is some lifetime of the quasi-particles. However, position of the peaks of the imaginary part of susceptibility as a function of Q corresponds to the spectrum, and the line width, namely width of your peak, corresponds to the inverse lifetime of the quasi-particles. This is how spectrum of elementary excitations are measured. What then happens for antiferromagnets? For antiferromagnets, it's pretty the same. Above critical temperature, you have a full isotropy. Your vector covers whole sphere. However, below critical temperature, you break the same SU2 symmetry. And you have pretty the same property for ZZ susceptibility. However, what is interesting, plus minus, how can I get antiferromagnetic magnets? You need to measure staggering component. The staggering component, this -1 can be incorporated by considering this naive state at certain vector, and in particular, you consider the susceptibility at the wave vector, which is slightly deviating from the reciprocal vector pi over a, pi over a, pi over a for the simple cubic lattice. For different type of barrel lattices, the reciprocal vectors are different. So if you consider this susceptibility, then you will get the same omega squared, omega plus I delta squared minus CQ squared. So this is the way to measure dispersion of antiferromagnetic magnets. So you need to measure susceptibility at certain wave vector and small deviations from it. Now, having said that, let me now comment a little bit about behavior, static and dynamic susceptibilities at temperatures above critical temperature, when we have isotropic situation. So, first of all, static susceptibility. Everything what I'm saying is related to T over Tc. First of all, ferromagnets. On Monday, I derived you that static susceptibility Q0 at temperatures close to the critical one behaves as C over T times 1 minus Z J S S plus 1 over 3T, 1 minus Q squared A squared over 6. So in total, we have C over Tc, 1 over T minus Tc over Tc, plus Q squared A squared over 6. Where Tc, which is a Curie temperature, is equal to Z J S S plus 1 divided by 3. I probably had some, no, correct. Okay, if we look at the same susceptibility for the antiferromagnets, in particular, this is a small q. Chi at q equal to 0, 0, and I'm not specifying which susceptibility because I have a full isotropy. This will be equal to C over T, 1 plus J modulus S plus 1 divided by 3T, 1 minus Q squared A squared over 6. So in the limit Q equal to 0, this is C over T plus Tn. So in the limit Q equal to 0, this is C divided T minus Tc, where the Néel temperature the only difference you see that in a simple cubic lattice I have all J's negative and here all J's are positive. So Tn, this is Curie temperature, and N says for Néel temperature, Néel, Curie, is Z modulus J S plus 1 over 3. So I can say that the static susceptibility chi minus 1 Q 0, 0 for ferromagnets behaves as 1 over T minus Tc. This is inverse susceptibility. For the antiferromagnets, it behaves as C over T plus Tn. Sometimes in literature, when people speak about static uniform susceptibility, people, as a jargon, says that the antiferromagnets are behaving like ferromagnets with a negative temperature, negative Curie temperature. So this is minus Néel temperature. Of course, we don't have negative temperature. What we observe is this cut here. While the course goes to 0, it requires 0 value at final temperature for the ferromagnets. And this occurs because, as I said, the uniform magnetization is nothing for antiferromagnet. It's conserved quantity, but it's not critical, because it is equal to 0 above critical temperature, and it is equal to 0 below critical temperature. While for the order parameter should be attributed to something which is 0 above critical temperature and non-zero below critical temperature. Therefore, what we need to do is to consider staggered susceptibility for the antiferromagnets. So the staggered susceptibility, namely K at Q minus P, A, if I now change Q by vector pi, I will have change of the sign to minus 1. Then, and this comes to the term here, what I will get, that this is C over T minus Tn, C over T, and plus Tn, 1 minus P square A square over 6. I do the same expansion. Therefore, in the limit of small deviation, P goes to 0, this is C divided by Tn, T minus Tn over Tn, plus, sorry, no, I'm not correct saying that, so this is plus, I already subtracted Tn, plus Tn q squared a squared over 6. Now it's correct. Plus q squared a squared p squared over 6. It's p. It's small deviation. So again, you see, if p is equal to 0, therefore you measuring your susceptibility exactly at the reciprocal vector pi, 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 1, 1, 1, you get that your susceptibility diverges when you approach to the critical temperature. So instead of susceptibility at small momentum, you need for antiferromagnets consider small deviation from the reciprocal vector, the q vector at which instability occurs. So this is the difference. So we have the same sorts of Einstein-Cernan theory which describes fluctuations in the antiferromagnets the same way as it describes the fluctuations in the ferromagnets. The uniform susceptibility, as I said, is still kept because you have the same property as I discussed here. Now, dynamical susceptibility above critical temperature for ferromagnets and antiferromagnets. First, dynamical susceptibility for ferromagnets above critical temperature. Ferromagnets. As I said, the mz operator, which is sum over n s and z, commutes with the Hamiltonian. Since it commutes with the Hamiltonian, then dmz over dt is equal to 0 plus some corrections to it. And these corrections start with the gradients of the magnetization vector. So this is d. Since one can show that the first derivative doesn't exist, this is mz. Well, in principle, z is absolutely senseless notation. You have your magnetization vector, which is isotropically placed on the sphere. So the equation for dynamics of magnetization is just a diffusion. So here we have a Laplace operator, and here we have a time derivative. This is diffusion equation. Diffusion means that the susceptibility, which is related to spin-spin correlation function, as I said, will get a pole omega minus dq squared. It's better to write it this way. If you take a Fourier transform of this function, this is e minus x squared over 4 dt. Diffusion is a sort of random walk where the square of the mean distance is proportional to the time. In literature, there is enormous literature about diffusion, about random walks on a lattice. For those who would like to learn more, read about that. However, we still need to obey Einstein-Cernan theory. This is q squared plus inverse correlation length squared. So there is some constant. This is how dynamical correlation function q and omega for ferromagnets behaves at final frequency at final q. You see that there are two limits. First of all, if you take omega equal to 0, then we reproduce Einstein-Cernan theory. But for finite omega, if you take q equal to 0, you see that there is a q square over omega, it's purely imaginary, and it's proportional to the correlation length squared. And I remind you that correlation length squared is equal to minus squared. It's 6 tau over a squared. Tau is t minus tc or t minus tn over tn. So this is correlation length. It's inversely proportional to the square root of tau. So this is how susceptibility for ferromagnets behaves. For antiferromagnets, if we are considering Néel state, which is sum over m s m z minus sum over m s m z. This vector doesn't commute with the Hamiltonian. Therefore, its dynamics dn over dt starts with a linear term. This is minus, in literature it's denoted Gaussian node, divided by susceptibility times n. So this is diffusive dynamics, this is relaxational dynamics. The order parameter doesn't commute with the Hamiltonian and is not conserved. It means that the antiferromagnetic dynamical susceptibility or Green function behaves as minus I omega of gamma plus q squared plus psi minus 2. Typically, it is attributed to so-called antiferromagnetic fluctuations above critical temperature, and the theory of high temperature superconductivity based on the antiferromagnetic fluctuations is on the market in one of several strongest candidates to be correct, their correct theory describing high temperature superconductivity. I will come back to this point on my last lecture, but I am giving you some information which you will need to digest the lecture with slides. Okay, now a few comments about anisotropic models. Anisotropic models. Is it clear what I'm saying? So the susceptibility provides information about spectrum if you are in the quadrant phase. In the paramagnetic phase, you don't have any magnons. However, you have either diffusion or relaxation if your temperature is larger than the critical one. These are not quasi-particles, because quasi-particles are corresponding to the energy spectrum. There is no real energy spectrum here. There is minus I omega, not omega minus something. So the poles of your Green function lie on imaginary part of the frequency. So this is not the spectrum. However, this is how we can describe dynamics of ferromagnets and antiferromagnets in the paramagnetic state. Okay, anisotropic models. Few words. So I considered on 2 lectures this Heisenberg model. Let's introduce anisotropy. Let's write yet another Hamiltonian which will be minus sum over n m j n m per s n plus s n minus 1 half plus s n minus s n plus minus sum over n m j n m z s n z s m z. So I introduced 2 coupling constants instead of 1, j n m perpendicular and j n m z. If the constant in the perpendicular direction is larger than the constant along z direction, we call it easy plane. Anisotropy. Because the main interaction occurs in the plane perpendicular to z direction. However, if we have opposite condition, if g and m z is larger than g and m perpendicular, then we are talking about easy axis anisotropy. 2 opposite cases. If, for example, the interaction in perpendicular direction is equal to 0, so extreme case of easy axis. is Hamiltonian minus sum over n m, g and m z, s and z, s and z. This is so-called Heisenberg model. You have only interaction of the moments along z direction. I think you will get a lot of discussion and a lot of calculations about Heisenberg model in the course of advanced statistical mechanics. Because Heisenberg model is one of the exactly solvable models. It can be simply solved in one dimension. One needs to sweat hard to solve it in two-dimensional situation, but it's doable. It's still unsolvable problem in three dimensions, and people build supercomputers in order to find a solution of three-dimensional Heisenberg model. You see that the model looks pretty simple. Spin 1/2, two Pauli matrices diagonals. Still in three-dimensional situation, Heisenberg model is still unsolved. The limit, so this is j top is equal to 0. Now let's take the opposite limit, gz equal to 0. Then we have a model minus n m s j top n m s n x s n x plus s n y s n y. This is yet another interesting model, which is called XY model. Again, in two dimensions, the investigation of XY model resulted in very interesting discovery, which is known as a Kosterlitz-Towers transition. Being here, you attended a colloquium of Nobel Prize winner Kosterlitz, who actually introduced you into the topic of Kosterlitz-Towers transition. The Kosterlitz-Towers transition has to do with formation of vortices, topological defects, and it goes beyond Landau paradigm of the phase transitions, namely the correlation length for the Kosterlitz-Towers transition behaves exponentially when you approach to the critical temperature, contrast to the power law behavior which I discussed. Again, I need one separate lecture to introduce you to the Kosterlitz-Towers transition, and at least 2 or 3 lectures in order to demonstrate you how exact solution of the Heisenberg model in 1 and 2 dimensions look like. Then, if you add magnetic field to, say, you consider one-dimensional Heisenberg model, just a chain of Heisenberg spin, it's very paradigmatic model for quantum computations, also for studying Limbland dynamics in the presence of Bach. But if you introduce the magnetic field which is perpendicular to direction of alignment of your spins, you involve second generator, second component of spin, x and y, and therefore you immediately make your problem quantum. So the classical model, which is one-dimensional sigma model in the absence of magnetic field, becomes immediately quantum model. And this is the way the quantum phase transition have been discovered by Michael Fisher and Pierre Petit in 1974. I'm very happy. In the early stage of my career, I was working with Pierre Petit in France, and this is a great scientist who made really great discovery. So the quantum nature of the phase transition was first discovered by studying the Heisenberg model in the transverse magnetic field, one-dimensional model in the transverse magnetic field. So that's basically all. I will probably leave discussion of the Heisenberg model till the slide lecture, because Heisenberg model is yet another paradigmatic model which actually result in the Heisenberg Hamiltonian when you consider certain condition for the Heisenberg model. We will have this discussion with slides when we discuss high temperature superconductivity. So, with this I conclude the chapter of the magnetism. The last lecture, Friday lecture, will be with slides, and I am telling you that there is a lot for self-education, for studying. 4 lectures is definitely not sufficient to give you deep course of quantum magnetism, but luckily you have time, you have book, and if you have intention to study it, I will be ready to give you advice what kind of literature read and what kind of calculations to do. Thank you. If you have any questions. You don't have questions, therefore we meet on Friday with a slide presentation about behavior of strongly correlated system, high temperature superconductors and heavy fermion compounds, and recent development of the quantum theory of superconductivity and magnetism. Good. Yes?
Yes. I don't know if others received the last slide you presented. I didn't receive it. I don't know if you can send it.
Which slide? You mean slides about Fermi-Bose systems?
Yeah, exactly. Yeah.
Because I have only slide lecture 1. After finishing on Friday, I will send you a link to the Dropbox where the slides will be located. But as I told you that nothing what will be presented on the slides, neither lecture number 10 nor lecture number 20, will be put as examination question. So nothing from what I'm showing on slide will be asked on exam. These 2 lectures, which is summary of what we have learned on the blackboard and showing you experimental devices and recent development. This is for your education, for your information. This is not what I'm going to ask you during the exam. Okay, we are done. Thank you very much. See you on Friday.
Thank you. See you.